go. Okay. So yeah, so we'll talk. Mixture models, okay? Mixture models is basically our observations come from a mixture of a mix of distributions. Okay? So, for example, one is we could say like heights of people, okay? Heights could be, we could say heights is a mix of two normal distributions. And we would have, one is for, one is for men and one for women. Okay, so that would be an example, right? Or another could be, you could have, if we're talking two-dimensional data, you could have some data points over here, okay? And then you could have some data points, over there. And we could say, these points come from, one come from a, multivariate Gaussian. Right? So, the mean is right there with, so you've got normal with, a mean and a sigma matrix, okay? And then you've got another set of points, right? And this will also comes from normal distribution with the mean mu and another standard deviation there, okay? Let me save this. Okay. And likewise, so here okay, and basically we have two different distributions. Okay, so we'll say each kind of component has a distribution. And we could say, we can kind of generalize this, and we could say, the distribution is the probability of x sub n given some set of parameters, delta, okay? So, each component has a distribution, p of x sub n given delta, okay, where delta is just equal to the parameters that define the distribution, okay? So in our case, we could say, so if it's, if we're talking about a multivariate normal, we would just say the probability x sub n given delta, it is, kind of the normal distribution with where delta, in this case, delta is equal to your mu and your sigma matrix, right? Is that okay? So all we're doing is we're just going to say each distribution has its own distribution, right? And it doesn't necessarily have to be Gaussian, doesn't have to be normal, but But for simplicity, we'll just stick to the normal distributions, because I think it's easy to think of mixtures of normal distributions here. Okay. All right, is this all right? Okay, and then, and so to make it a mixture, we have a bunch of these, so each component class, so we'll say each component K has its own kind of distribution, right? So, for K equal to 1, we have probability of x of n given delta 1, okay? And then for K equal to 2, we have probability of x of n given delta 2, okay, et cetera, et cetera. So just for K, we have probability of x of n given delta sub K. Okay, and then we have a mixing proportion. Okay. So the mixing proportion, this is pi sub k, okay, where and the rule is when we add up all the pi's, it has to equal 1, right? So we'd say, the sum of pi sub k is equal to 1 for k equal to 1 to capital K. Yeah. All right, so, example. It could be, oh no, that's fine. All right, pi sub k, we could say, if let's say we're talking men and women again, I don't know, maybe pi sub men, we'll just say pi 1 is equal to, I don't know, what proportion of the world is men? Like 49%? Something like that? I don't know. Are there more men or women? There are more women, right? Yeah.
Men die faster.
Yeah. Okay. On average. Okay, so it could be something like this, right? Okay, or and then we could have if we're talking about heights, the heights could be, I don't know, mean 70 inches and standard deviation 3. I'm making this up, and mean 64 inches, standard deviation of 3, or something like that, right? Okay, or this might be like the general, okay? But then, if we go to like the engineering school, okay? So if we go to the engineering school, this is the mixture component there's more men. I don't know, what are the proportions of men in the engineering school? I don't know, 70%-ish, something around there. Okay, so then here we would have 0.7, and then women would be 0.3, and thus and we could still say it's still normal, 64 and 3 or something like this. Okay, and so thus the resulting distribution here would probably look something like this, whereas over here it would probably look, I don't know, this is exaggerated, but it would look probably more like that. Yeah? Not so wiggly, but something like this. Okay, and likewise, depending on how our proportions are defined, our data set could look, if one of the proportions is low, you might just have a few points here, and then you have a whole bunch of points coming from the other thing, right? Or it could be, so this is, pi 1 is, you know, like 0.2, and over here you have pi 2 is equal to 0.8 or something, okay? And then, of course, you could have more proportions, okay? So anyway, the probability of any given point, the total probability of some x sub n, this is going to be equal to the mixing proportion pi 1 times the probability of x of n for class 1 plus pi 2 times the probability, you know, that density for class 2, so on and so forth, et cetera, until you get to the last component. So, you know, in my pictures I've only been drawing 2, but you could have, yeah. So we would summarize this and just say the probability for some data point is going to be the sum across the mixing proportion times the probability given the parameters that define it, delta k. Okay, so from k equal to 1 to a total of k components. All right. So this is our mixture model. All right. Is this okay? The probability of any one given data point is going to be basically the density for a particular class multiplied by the probability of that class. Okay, and then thus the total likelihood of our entire data set okay, if we assume every observation is normal, the probability of the entire data is going to be the product of all of our data points, n equals 1 to n, of this. Okay, so this is our likelihood, okay? I mean, we could further define it with all of these things. All right, is this okay? This is our likelihood here. Okay. And okay, so now we've got some data set that's a mixture, and we want to be able to parse out. We've got to figure out, you know, our component mixtures and then the respective distributions here, right? So what we have to do now, okay, so, you know, trying to estimate the parameters. Of the mixture model, okay? So, you know, we have to estimate the proportions pi sub k, and then we have to estimate, you know, the parameters, which include mu sub k and sigma sub k, okay, for each, and we have to do this for each component class k. Now, if we have data like this, okay, maybe visually, what we would do as people, we would say, oh, you know what, I'm going to identify these two components, okay? So, if we were people, as people, we would identify the clusters. And then we would probably do maximum likelihood estimation for each cluster that we've identified, right? Okay. So that's what we would do as people, right? And that's if we can tell the difference between one set of data points and another, right? If we can easily identify the clusters, this would be how we would do it, right? But the trick here, or not the trick, the problem is that we don't know to which cluster a point belongs, okay? Okay. So we have something called a missing variable, okay? Which we will call z sub n, okay? We have a missing variable, which is the identity of which cluster a point belongs, okay? Z sub n, this will be the cluster, I guess the cluster membership of a point. Okay. And so this is what we want to try to figure out. And so this is, and so we're going to have an iterative process, okay? Which is, we're going to try to estimate the cluster membership, and then once we have the cluster membership, then based on those cluster memberships, we would kind of do maximum likelihood estimation, right? So we iterative process, okay, which is, we try to figure out membership, okay, and then based on the memberships, we update the distribution parameters. Okay, and then we update class memberships. Okay, and then repeat. Does this kind of make sense? Right? so it's sort of similar to k-means clustering, right? K-means clustering, the way we did class membership assignments was we said you are assigned to whichever cluster has the closer mean. And then once we did all of those assignments, then we updated the location of the mean. And then we did the assignments again. And we said you are assigned to whichever cluster has the closest mean. And then we update the location of the mean, and we do this back and forth, right? So so the iterative process is kind of the same for k-means, okay? K-means clustering. And I just kind of want to make sure that makes sense there, okay? So, very similar k-means, except it's different, right? So very similar to k-means. K-means clustering the class membership assignment was deterministic, okay? We said, you belong to the class, or you belong to the cluster whose center is closest. Okay, and then you update the centroid and repeat. With the EM algorithm, when we figure out the class membership, this is going to be probabilistic. Probabilistic. I don't know how to spell this. Okay. Okay. And the figuring out of the class membership is probabilistic, and it works in a way that's very similar to naive Bayes classification. Okay? So if you understand naive Bayes classification, I think this part will make a lot of sense, right? And if we didn't quite understand naive Bayes classification after doing our homework, then we might be in a little bit of trouble. But so we try to figure out class membership, but the class membership assignment, this is probabilistic, and this is what we call the E step, the expectation step. It's kind of like what we would expect. The expectation on the class membership, and we get a kind of a probabilistic class membership. Okay, and in our textbook, so the textbook goes through a bunch of derivations for doing this. I'm kind of cutting to the end. All right, so our class membership, this is kind of our expected class membership, which we will call Q sub nk. All right. This is, this is equal to, the probability, kind of the expected probability that observation n belongs to class K, right? So this works kind of like naive Bayes, and we would say that this probability, we can think of this as the probability that the membership of znk is equal to 1. This is that the membership of observation I, or observation n, belongs to class K. Right? So z n1 is equal to 1 if k equals 1 for n, or z n2 equals 1 if the class membership, if n belongs to class 2. Okay, so this is the probability that observation I belongs to class K, given the values of x of n, the probability vector pi, and the parameter vectors delta. Okay. Is this okay? Am I losing you with all of these symbols, or are we still okay? We're still good. Okay. All right. So think naive Bayes. How does this work with naive Bayes? Okay. This would be the probability that z and k is equal to 1 given, this is kind of like our prior times our likelihood, and in this case, if we're dealing with a Gaussian, we've got mu and we've got sigma, yeah? And this would be the kind of the Gauss density. Okay. And then, so this goes in the numerator, right? We have our prior multiplied by the density, or the likelihood, Gauss density, kind of to get our likelihood. And what goes in the denominator? The marginal, right? And how do we get the marginal? Basically, it's just we add up for every possible class, right? So this is the marginal, which is equal to the, basically the sum of the numerators for every class. For all possible classes, okay? So what this becomes is in the denominator. So my numerator is, well, okay, I'll just copy the numerator again. Z and k equal to 1 given pi sub k times I'm sorry, this is not a vector, it's a matrix, sigma there. Okay. And then the bottom is basically the sum across all classes, but we would say to identify that this is for probability that z and j is equal to 1 for class okay. So here we would get kind of a vector of probabilities, right? It would say, based on the data and the current estimates of the center and the standard deviation, we would estimate this, okay? So actually, I shouldn't say this is a naive Bayes. It would be more like the Bayesian classifier. It's not naive Bayes because we're not making the naive Bayes assumption. We're going to just, but this part is a Bayes classifier, right? We are estimating the probability that it belongs to class K based on our current estimates of those class probabilities. I mean, of those class parameters. Okay. This part is the prior part is going to just be my pi sub k for that class, okay? And then so here, basically now I just have and then this would be the sum across Is this okay? So basically, I'm using a Bayes classifier to give me estimated probabilities that this point belongs to this cluster or this cluster or this cluster. So based on my current estimates of, the cluster center and spread, I'm getting now probabilities that this particular point belongs to each of the clusters, right? So you created your naive Bayes classifier, and so every point, when you run it through the classifier, gives you a vector of probabilities, right? And it might be like 99% it's Setosa and 0.5% Virginica and 0.5% Versicolor or something like that, yeah? We might get something, especially when we're iterating this, these things could end up being different things, okay? And then we're going to use this, our expected class membership, okay, which is not a definitive you belong to this cluster, you belong to this cluster, but rather we have a probability that you belong to this cluster and a probability that you belong to this cluster. We use that to kind of weight the values in each cluster, and then we use those weighted values to come up with maximum likelihood estimates. Okay, so we have our expected class membership, okay? And then now we have the M step, which is, our maximization step. So this part is basically we perform maximum likelihood estimation of the distribution parameters based on our class estimates. Okay, but the key here is that our class estimates are not defined, okay? Our class estimates are not saying you definitely belong to this class and you and only this class, okay? Our class estimates are probabilistic. Okay, and because they're probabilistic, we're going to get kind of like, weighted values on our data points to do our maximum likelihood estimation. Okay, so okay, and so so for example, the pi sub k. This is our kind of our class, the probability, kind of our probability that a data point belongs to class K. If we had the actual assignments, this would just be the count of the data points in K divided by the total number of data points, right? So if we have the actual class assignments this is, count of n and k divided by total n. Okay. With the probabilistic, okay, we don't have the actual class assignments. So this just becomes the sum of Q and K for a particular K, right? The sum of the probabilistic assignments, probability assignments, for class K. All right. So what this might look like is, if you have, let's say I have 4 data points, just to keep it really simple, okay? And it might be, okay, so in reality, my pi sub red would be 0.5, and my pi sub blue is 0.5, okay? This would be if we know the actual assignments, okay? But what we have here is with the probabilistic, point A or point 1 might have the class probability for A and B might be like 0.9 versus 0.1. And then point 2, the class probability might be 0.9 versus 0.1. And then point 3 and point 4, my A here, maybe 0.3. It's a 0.2 versus 0.8, and then 0.4, maybe it's 0.15 versus 0.85. Okay. And therefore, my pi sub A in this case would be 0.9 plus 0.9 plus 0.2 plus 0.15 divided by 4. Okay, and then so instead of being 2 divided by 4, I have, I don't know what this is, 2.15 over 4. Okay, and then probability of B would then be 1.85 over 4. Okay, so we get my proportions are based on the probabilistic estimates of these data points. Okay. And then so with this in mind, we can now also perform maximum likelihood estimation. Okay. So normally, if we were doing maximum likelihood estimation, we would just say, oh, I only have these 2 data points. I'm going to try to maximize my likelihood based on these 2 data points. Now we're saying we've got all 4 data points, but these ones are weighted heavier and these ones are weighted less. Now try to maximize your mean and maximize your standard deviation based on that. Okay. All right, and then so the other components, okay, so the MLE estimates for mu, or let's just, for mu sub k, based on the weighting ends up being, you're going to take kind of your probability, expected probability q sub nk, your expected class membership, multiplied by x sub n. This is, right? And then you're going to divide by the total sum of q sub nk. All right, so this is basically it's like the weighted mean. Okay, weighted mean of x. For class K. And then you do same thing, maximum likelihood estimate for sigma. It's going to be, I guess, sigma sub k. So it's q sub nk summed up, and you just do xn minus mu sub k, the mean, times xn minus mu sub k transpose. And again, divided by q sub nk, total number of points, estimated number of points in that class. And this is kind of like a weighted covariance matrix. Okay, and we weight based on kind of our Bayesian classifications. Okay. It feels a little bit. It feels a little strange at first, maybe. Okay, or maybe you totally feel comfortable with this. Okay, it might feel a little bit strange, but again, the idea is, with k-means clustering, the classification was deterministic. It was this centroid was the closest, therefore you belong to that cluster. Okay. Over here, the cluster assignments are probabilistic, and we're saying, based on the mean and standard deviation of this cluster, we've got an 80% chance of belonging to this one and a 20% chance of belonging to that cluster. Okay, and we take that into account when updating our mean and our standard deviation of each cluster. We say, okay, use this point, use it about 80%, okay? And use this point to update that cluster and use it about 20% is kind of what we're saying. And we do a probabilistic updating of our mean and standard deviation that way, okay? And, coding it up is actually rather straightforward as long as you understand that we're dealing with probabilities, okay? And then you have to do it that way. Yes? Oh yeah, it's going to be much better, okay? So kind of in your final in your final exam project or whatever it is, I'll have you guys code up a maximum likelihood estimation algorithm, okay? And you'll see how it outperforms k-means clustering because it takes into account also the standard deviation there. Okay, we'll end here for today, and then next week, I don't know. I'll look up some fun things for us to do.